Hi everybody. What I'm going to introduce here are the ideas that are going to be behind the integrated rate law. And so we're going to start to get into a little bit of calculus, but you're not going to really have to know the calculus. If you can understand it, great, but don't worry so much if you can't. So let me move our title out of the way and let's just remember where we've come from. So with the differential rate law, what we've done with that rate law is we've articulated how concentration and how ideas like temperature will affect a reaction's rate. Now we've overtly seen the effect of concentration because we've written these rate laws that look something like rate equals, say, K times the concentration of A squared times the concentration of B. And so we can overtly see the effect of concentration. And think about this. If I were to double the concentration of B from one experiment to the next, what would be the corresponding effect on the rate? Well, if B is first order as it is with respect to the reaction, then a doubling of the concentration of B will lead to a doubling of the reaction rate. What if I were to double the concentration of A between two consecutive experiments? Well, since the order with respect to A is squared, then when I double that concentration here, I'm going to see a quadrupling of the rate. Now we haven't really seen it yet, but the effect of temperature on the reaction rate is actually buried inside of the rate constant, and that's a detail that we're going to get into later on. So let me get these guys out of our way for now, and let's talk about the integrated rate law. Now the integrated rate law is where we're going to connect the idea of concentration to time. So let's say I want to know how fast a reaction is, or not really so much how fast a reaction is, but how much concentration I have of, say, my reagent A at time equals, say, 5 minutes. It's the integrated rate law that's going to allow me to answer that question. Or I could reverse the kind of question. Maybe I want to know how long it's going to take half of my reagent to go away. That idea of taking the point at which half of the reactant has gone away, that's referred to as half-life, often abbreviated with T sub 1/2. And we'll see that concept as we go in. Now, I'm going to start to go into the details of this in the next video. I just want to introduce the ideas here. But keep in mind that what we're going to look at is we're going to look at first order reactions, and you'll see what that means in greater detail, second order reactions, and zeroth order reactions when we look at the integrated rate law. And we'll get into the details of the math of those. And again, we're going to see a little bit of calculus as we do this, but don't worry so much about that. I'm going to have some, excuse me, sort of summative information about all three of these order types with respect to the integrated rate law. And then it'll be that summative information which is really what you're going to want to know. All right, so we're going to get into first order reaction, first order integrated reaction rate laws in the next video.